Well, greetings, everybody. How are you all doing today? Happy Tuesday, happy noontime, wherever you might be. Maybe it's a little later where you are. John Barba with Takeo Comfort Solutions. I'm joined by Dave Holdorf, who is also on camera, and not on camera is Rick Mayo, and Rick's out there as well. We make up 60% of the Takeo training team. Takeo has 5 full-time trainers, so we're here to help you guys out. I want to make sure everybody can hear me okay and that your sound is working. Um, what I would like you to do is, if you can, just on your control panel on your screen, there should be a little arrow, orange arrow, and if it's pointing to the left, click on it. That'll expand your control panel. And just do me a favor, where it says down at the bottom where it says questions, just type in a hi, hello, how are you? That now means you can hear me okay and see me okay. Great, everybody's doing fine, outstanding, very, very good. This is also where you're going to ask questions. So as we go through the program today, guys, please ask whatever questions you have. Guys, girls, I apologize. I tend to make it a blanket statement, but anybody out there who's listening, please feel free, ask any question you want as as we go through this, and we'll do our very best to answer them for you. We'll try to get to as many as we can. If we can get to all of them, great. If we can't, we'll do our very best to give you the opportunity to email us and let us know. This program is going to be recorded and it will be made available to you. You're going to get a follow-up email tomorrow from us, and it'll include a link to the recording, so you can go back and rewatch it as many times as you wish. So what we're talking about here, what we're going to talk about here is sizing, piping, and pumping for indirect water heaters in residential applications. The theory can certainly be expanded into commercial applications, but this is going to be understanding what the specification sheets tell you in terms of what they tell you in terms of performance, and how you really have to be careful when you hook these up to a boiler. How do you size the boiler in relation to the indirect water heater? How do you size the circulator that's going to be connected to the heat exchanger for your indirect water heater? And how is that piping going to be sized as well? A lot of that stuff is going to be very important as we go through the session today. So as we can see, everybody kind of has the idea of how to use the question section. Again, as they come up, please ask whatever questions you have. Now, this program itself kind of got its start long ago in a galaxy far away. A former colleague of ours was building a house, and he was one of these guys who was always looking for a deal, and he would work whatever contacts he had to get whatever deals he could get for whatever he wanted. And he was using me to help him design his heating system. And as I was looking over his heating system, I saw the master bathroom, and in the master bathroom he had a bathtub that looked kind of like that. And I asked him, well, what are you going to be using that for? And he gives me that nudge and wink and says, you know what I'm going to be using that for? I said, well, terrific. That's awesome. What are you going to be using for a water heater? And he goes, you're not going to believe the deal I got. The gas company is going to give me for free a 40-gallon water heater. Well, what are you going to do with that? I asked him. I mean, that's nice that you got it for free, but you can't use that tub. You're not going to fill it. He goes, oh, we'll just use it. We're just going to use the tub maybe once a month. And I said, no, you're not. You're not going to be able to fill the tub. The water heater doesn't have the capacity to fill that tank, nor does it have the recovery to kind of keep up with the spout that you're going to have to put on that to be able to fill it up in a reasonable amount of time. It's simply not going to work. And he got a little upset with me because he was accusing me of trying to force him to buy something he didn't need, which was silly because I didn't really care. It was not I wasn't selling him anything. We were colleagues. He says, no, I don't really care. What I want you to be able to do is to use that tub at all. I want you to be able to make use of it. If you're going to put it in, you might as well have enough hot water to fill it up. Finally, I had to explain to him, I says, if your wife wants to use this tub, and that's what she's going to look like because she can't fill it up with hot water, then this is going to be you. You're going to be taking some cold showers. I'm sorry, that's just the way it is. He had a fundamental problem. and it was an arithmetic problem. That's what was going on here. It was all math. It was an arithmetic problem. He didn't have enough storage in that tank for a dump load to fill that tub, nor did he have enough recovery to make up for his lack of storage. So it was a double whammy. He was not going to be able to use that tub. I finally convinced him that the tub was a waste of money unless you had a water heater that was capable of filling it. Oddly, that's a very common challenge that one has when trying to make the case for the water heater. You got to have enough of stored water to dump into that tub to fill it up, and then you have to have enough recovery to continue to deliver hot water throughout the rest of the house or into that tub. So that was the problem. What we're going to learn today is how to interpret the data that we see in any spec sheet from any indirect water heater manufacturer. What do all those numbers mean, and how do they impact performance? Once we understand that, we're going to learn how to size the circulator that we need for the coil in the indirect, as well as learn how to size the pipe. Now, there's a common mistake made in pipe sizing, and we will address that today as well. And then we're going to look at an option or two that might help you to get a little bit more out of an indirect water heater. Specifically, potentially an existing indirect water heater that might not be keeping up with the demand of a specific application. We'll show you a couple of tricks that you can use to boost that indirect's performance. Right. And again, as I said, any questions you have, please feel free to just chime on in, and we'll do the very best we can to answer them. Let's start with the spec sheet, if we may. This is a spec sheet from Superstore, and not to endorse Superstore or anything. It's just a brand that we were able to find a spec sheet for, and they all pretty much have most manufacturers have essentially the same information in their spec sheet. What they tell you is obviously the model number. That's important to know. Some dimensional data. Then it tells you the capacity of the tank in gallons. You also get the heat exchanger surface area, the recommended flow rate through that heat exchanger, as well as the head loss or the pressure drop through that heat exchanger in feet of head. All right. And then next we have ratings. Okay. Next we have ratings. We have ratings for 180-degree water, boiler water, first hour ratings, and 200-degree boiler water, first hour ratings. That would include the recovery plus the stored capacity. Now you'll notice if we go back one, there's two charts here. There's a top chart and a bottom chart. And in this example with Superstore, the top chart's the happy chart. The top chart is the one that tells you you're bright, you're good looking, and have a wonderful future ahead of you, okay? The top chart gives you all the happy news, okay? Or in the way we're going to phrase it here, the top chart giveth. The top chart giveth. All right, if you take a look at the SSU 45, which is what we're going to look at, we see we have 45 gallons on hand. That's a 45-gallon tank. Okay, that's pretty cool. If we take a look at our 180-degree boiler water first hour ratings, storing the water at 140 degrees, we've got a first hour rating of 212 gallons. Hokey smokes, Bullwinkle, that's a lot of water, okay? So there's 45 gallons on hand, and over the course of the first hour, I have 212 gallons, or if I stored at 115, which you shouldn't, but you do, it's 292 gallons first hour. You look at that and you say, whoa, what's not to like? This is a great little indirect. This is everything I'm going to need. Well, that's the top chart. The bottom chart holds you accountable. If the top chart giveth, the bottom chart taketh away. Now, and it taketh away in a very sneaky manner. You start out with a lot of dimensional data, okay? 9 inches from the floor to the boiler supply, 4.5 inches from the floor to the boiler return. Okay, terrific. The domestic hot water out, that's 46 inches up off the floor. 3/4 inch NPT male domestic connections. You got your working pressure, you got your shipping weight. Way over on the right-hand side, it tells you to get the performance that we talked about in the upper chart, you're going to need, if the boiler water is 180 degrees, you're going to need 141,000 BTU net output boiler. That's the AFUE of the boiler. 141,000 net BTU output to get the 180-degree boiler water performance. That was 212 first hour gallons at 140 or 292 first hour gallons at 115. If we go to the 200-degree boiler water chart, we'd need 161,000 BTU boiler. So we've got to have that boiler size to get the performance that we were talking about. This goes back now to the question, do we size? Because, you know, imagine a house needing 141,000 BTUs. It's going to be a big house, right? Most of the times, in most normal residential applications. Now, I'm not talking the McMansions and the mountain ski lodges and things like that, but in a normal residential application, you may very well be dealing with a heating load well below 100,000 BTUs. Now you have a question: do I size the boiler for the domestic hot water performance load, or do I size the boiler for the indirect? Okay, I'm sorry. Do I size the boiler for the heating load? Is it sized for the indirect or is it sized for the heating load? We're going to take a look at both, and hopefully you'll be able to make a determination as you go through the process. All right. So again, 141,000 BTU net output at the boiler in order to get that 212 first hour gallons at 140 degrees stored water temperature. What does all this mean? Well, where do these numbers come from? It comes from basic math. Again, all of this is boiled down to a math problem. All right, we're talking about a math problem here. The first part we have to understand is, yes, I have 45 gallons in that tank, but I don't have 45 gallons in that tank, if you know what I'm talking about. In most water heaters, about 75% of that tank's capacity is usable at the water temperature that you want. All right, if I've got 45 gallons in that indirect, only 75% of that is usable before I reach what's called the drawdown. Because when you start taking hot water out, you're replacing that water with cold water. And that's going to be cooling that thing down, et cetera, et cetera. So at most, I have about 75% of that tank as usable hot water at the temperature I want. Okay. What causes that? It causes cold water. Then you've got coil space too. Don't forget the coil space in there that takes up some area. All right. So about 75% is usable capacity. To figure this out, if I have a 45-gallon tank and I want to find out how many usable gallons I have, simply multiply by 0.75, and that's going to tell me I have 34 gallons of 140-degree hot water available in that tank. Just 34 gallons, and that's what I got to work from. Okay, that's my dump load. That's what I got. Boom, shoot it out. That's what I got. 34 gallons out of a 45-gallon tank. If it was a 40-gallon tank, it would only be 30 gallons. So yeah, you can certainly do the math. Now, let's talk about recovery. Figuring recovery. At what rate can that water heater recover? Meaning, at what rate can that indirect turn whatever the incoming water temperature is? We'll presume at about 50 degrees because that's the ASHRAE standard. At 50 degrees coming in, how quickly can I turn that 50-degree water into 140-degree water? So we're going to figure the rate of recovery. And figuring the rate of recovery is all about BTUs in gallons per minute. Not in terms of when we do hydronic heating, how many gallons per minute do I need to deliver to a radiator to get the BTU output I want? It's more along the lines of how many gallons per minute of hot water can I make with the BTUs I have available at the boiler. That's how we want to phrase this. That's how we want to look at this. So how many gallons per minute can I make with the BTUs available at the boiler? And fortunately, my friends, there's a math formula for that too. It's boiler output. This is your net boiler output, that AFUE number, not the IBR number, but the AFUE number for a boiler. It's the net boiler output divided by 8.33 times 60 times 90. 8.33 times 60 times 90. Now, what does that mean? Well, where do we come up with that? Well, 8.33 should be pretty simple. That's the weight of 1 gallon of water. 8.33 is the weight of 1 gallon of water. 60, of course, is the number of minutes in an hour. And 90 is the ASHRAE recommended, the DOE recommended temperature rise to use when figuring your capacity. 90 degrees. They're figuring 50-degree water coming out of the ground, and we want to heat it up to 140. So that's a 90-degree temperature rise. 90-degree temperature rise. If you're in an area like Alaska or something where the water's coming out of the ground colder than 50 degrees, well, then you have to adjust your numbers. But for our examples, and for the most part, 8.33 times 60 times 90 works for us. If we were to math that out, that comes to 44,000 and change. We're going to call it 45,000. Okay, so essentially the formula we're going to use is the net boiler output, the AFUE net, the DOE net boiler output, the DOE net boiler output divided by 45,000. DOE output divided by 45,000. That'll give us our rate of recovery. So let's do the math here. Let's go to that 141,000 BTU boiler. 141,000 divided by 8.33 times 60 or 90 or 45,000. 141,000 divided by 45,000 tells us we can recover at a rate of just over 3 gallons a minute. Just over 3 gallons a minute. For our purposes, we're going to call it 3 gallons a minute. All right, we're going to call it 3 gallons a minute. Now, how many minutes do we have in an hour? Well, of course, we have 60 minutes in an hour. So 3 gallons per minute times 60 minutes means over the course of an hour, I can create 180 gallons of water. I can recover 180 gallons over that hour, So if we were to factor this in, 34 gallons stored in the tank, plus the 180 gallons recovered, that's going to give me 214 first hour gallons. The spec sheet told us 212, close enough, okay? Close enough.
Yep.
That's where those numbers came from. So for that first hour, if I turned on a hot water spigot at our flow rate of 3.5 gallons a minute, all right, I could run for 1 hour that spigot and have nice 140-degree water at that spigot if I wanted to. Now, how would you want to? No, of course, because no one's going to take a bath in 140-degree water, at least not twice, okay? So that just gives us a starting point. We can run that spigot at 3.5 gallons a minute for that first hour and not drop off in water temperature. After that first hour, we'd have to choke it down to 3 gallons a minute. If I'm running at 3 gallons a minute, I can recover and be fine pretty much all day long. But 3.5 gallons a minute for that first hour, 3 gallons a minute nonstop after that. Now, obviously, we don't use hot water that way, right? We don't use hot water that way. There's a couple of big ifs here, all right? There's a couple of big ifs that we have to make sure we understand. This will all work provided that I have that 141,000 BTU boiler, provided that the piping from the boiler to the indirect coil and back again is sized properly for the performance that I need, and that I've chosen the circulator appropriately. It's not always 3/4 inch pipe and a 007, all right? Could be, but it isn't always, right? It isn't always. So we got to pick the right circulator. The pipe sizing has to be proper, and to get that performance, we need 141,000 BTUs at the boiler. All right, quick status check here, folks. How are we doing? Give me some feedback. Any questions out there that we need to look at, Dave and Rick, or any comments you guys would like to add?
I'm paying attention to the question board, so if you've got them, please type them in there right away. Rick is also. We'll type them back right away, and if we need to, we will interrupt John to get it into the presentation. So, so far so good on my end, John.
All right, Rick, anything you want to add?
Yeah, right along the same lines where you're going there, John. You folks, no names mentioned, but there was a real popular 41-gallon tank out there for a long, long time. And I think what John's going to show you here is that you might have the biggest brag about what the recovery rate is of something, but storage means a lot, and there's some things that we can do to get around storage, but if you don't have the capacity in the tank, you'll end up shortchanged quite a bit. And I'm just speaking to the same thing John was talking about. I've been out on jobs where people were just unsatisfied with what they were getting, even though they thought they were getting all kinds of recovery. So anyway, this is a good class. This is to keep you from having problems with some of the things we've all dealt with in the past.
There's
It's,
nothing worse than getting ready for a fun Saturday night and lighting candles and all that. You can't fill up the tub.
Yeah.
Yeah.
I mean,
And if people are experiencing this in their home, they don't do anything about it. They live with it. They keep it as an expectation and do not know that there can be anything done about it. So unfortunately for a lot of us out there, it's a self-inflicted wound that we're putting into people's homes because we're not paying attention to this math side of things. It works, like John was saying, we've got, that 3.5 gallons a minute should be all good, but this is where that expectation level is really low when it comes to domestic hot water people's homes. Their expectation level is hot on the left, cold on the right. They just don't know about the volume of water that they can get in their home and how much of it and how long they can get it. So when people run out, they live with it. So these might be the little things to pay attention. So if you're in somebody's home doing some work and not related to this, take a look at it and pay attention to it and where you might be able to offer correcting it for some applications that are out there.
very good, very good. All right, let's continue. Let's see what would happen if we went with a smaller boiler. Let's say we size the boiler not for the domestic load, but instead for the heating load. How does that change the water heater's performance, and how does that change what we can do? In this example, we're going to use, again, that formula, net boiler divided by 45,000. But in this case, we're going to use a boiler size for the house load, the heating load, which is only 75,000. So in this example, 75,000 DOE output divided by 45,000, that's going to give us a rate of recovery of only 1.67. It's a little more than half, all right, just a little bit more than half of what we had before. So we're recovering now at a rate of 1.67 gallons per minute. We multiply that by 60 minutes, our rate of recovery for that first hour is only going to be 100 gallons, all right, only 100 gallons as opposed to what we had earlier. Now, if we go back and add that to what we have stored, we have 100 gallons recovered plus 34 gallons stored, so that's 134 first hour gallons as opposed to 212. If we divide that by 60, now you'll see what happens. We can turn that spigot on to a flow rate of 2.25 gallons per minute and have 140-degree water coming out of that spigot for a full hour, all right? And then after that, we have to crank that down to a little bit over 1.6 gallons a minute in order to keep, in order for the recovery to keep up with the flow. You can see how that might change things a little bit. Now, all of a sudden, can you take 2 showers at the same time? And can they be long showers? You might be able to take 2 10-minute showers, but 2 15-minute showers might be out of the question. All right, can you run the dishwasher, the clothes washer, and take a shower at the same time? Those are going to be questions that you'll have to find out. Likely no. Okay, it's likely that you won't be able to. Now, again, we're not taking a shower in 140-degree water, right? We are mixing at the fixture, and that expands what we can do. All right. It's just a matter of where do we find that sweet spot? Where do we find that point where all of a sudden, okay, we can't keep up anymore. We can't keep up anymore. Good question from Kevin Hanlon. How many gallons in a typical hot tub? That's like how much does a typical bag of groceries cost? It depends on what you put in it. There's a whole bunch of different sizes. I'm thinking you're starting at about 80 to 100 in many cases. If it's a multi-person tub, those big ones. Otherwise, we've seen like just jetted tubs or regular bathtubs as well. They're regular size bathtubs. So it kind of depends on what you're looking at. So you just kind of have to again look at the specs of what you're trying to accomplish. So here we have 2.5 gallons a minute, all right, or 2.25 gallons per minute. Again, we should be okay. We should be okay. We think. Provided that we do the other stuff right. Now we have to look at the lower chart, or we have to look at the flow rate and the pressure drop, through the heat exchanger to make sure we size the pipe properly and sized our pump properly. Because if we don't do that, we're off the chart. We're only gonna get what we're gonna get, and that's when we're gonna start to have some issues. A lot of people will look at an indirect, and they'll look at the tappings for the heat exchanger, and they'll note that those tappings are 3/4 inch, and they'll say, well, 3/4 inch, I'm just going to run 3/4 inch here. Then why would it's a 3/4 inch tapping? Why the hell would I run anything but 3/4 inch? Well, that's the tapping. You still got to get flow, the appropriate amount of gallons per minute of flow to that heat exchanger. That 3/4 inch tapping, view that as pressure drop, and the flow rate through the heat exchanger is all pressure drop. That's feet of head. We have to factor that in. But if I need to get 10 gallons a minute to that heat exchanger, I need to use pipe that'll give me 10 gallons a minute, and that's going to be, that's going to be 1-inch pipe. But let's take a look at this, okay? If we take a look at the SSU 45, all right, we'll see right here. You can see right here that, all right, we're at 10 gallons a minute. We're 10 gallons a minute required flow rate through that heat exchanger, required flow rate of 10 gallons a minute through the heat exchanger, and the pressure drop through that heat exchanger is 7.9 feet ahead. So 10 gallons a minute at 7.9 feet ahead. Well, first off, 10 gallons a minute, that tells me I need at least 1-inch copper pipe. That's going to be about as much as I'm going to get through 1-inch copper pipe. So I got to run from my boiler to the heat exchanger 1-inch pipe. And if it's a 3/4 inch tapping, I have to drop down to 3/4 inch right at that point. And that will be the pressure drop. Okay. And then I got to run 1-inch back. Got to do it. If I'm only running 3/4 inch, I've cut my potential down considerably. All right.
Yeah.
I may be able to get 5 gallons a minute through that. That might be what I'm dealing with. So, and if I try to run more, I'm going to have velocity noise and erosion issues that I really don't want to deal with. So again, pipe sizing here is critical. Now, what if instead of this, I was going with my 75,000 BTU boiler, right? Only 75,000 BTUs instead of 141,000 BTUs. That's going to change my pipe sizing and my pumping just a little. Indirects, the output on indirects are based upon a 30-degree temperature drop. So 180-degree water going to that coil, 150-degree water coming back. If you've been through any of our programs before, you remember the universal hydronics formula, right? To figure out your flow rate, the universal hydronics formula states that GPM is equal to the BTUH divided by delta T times 500. Delta T is the temperature drop, right? And 500 is simply a mathematical constant that we use for 100% water. So 75,000 BTUs divided by 30 times 500, or 15,000, that's giving me a flow rate of 5 gallons per minute instead of that 10. So now I can use, it still should be, you might be able to get away with 3/4 inch pipe. Ideally, you'd probably want to be looking at 1 inch. Okay, you'd probably want to be looking at 1-inch pipe, because that would give you 2 feet of head loss. Instead of 10 at 7.9, you'd have 5 at about 2 feet ahead. If it was 1-inch pipe, which at 5 gallons a minute, it really should be. You could get away with 3/4, but the head loss is going to be a little bit higher. All right, and we'll see how that affects us later. All righty, so again, what does all this mean? We're talking 1-inch pipe, 5 gallons a minute, 10 gallons a minute. We're talking 1-inch pipe from the boiler to the heat exchanger and back again. All right, and we want to keep that tank close, not overdo it with fittings, keep the fittings minimal, etc. So we minimize the head loss that circulator has to deal with between the boiler and the indirect. Let's take a look at what that might wind up being. All right. So let's say my supply and return piping's 40 feet. It's 20 feet there, 20 feet back. Okay, that's how long of a run it is. 20 feet there, 20 feet back. I've got a bunch of 90s, and these 90s, a 1-inch 90 has the same pressure drop as 2.5 feet of straight pipe, right? So we figure that equivalent length, say 16 90s, 2.5 feet each, that's an additional 40 feet of equivalent length. So what I'm dealing with here is about 80 feet of equivalent length, all right, about 80 feet of equivalent length. To estimate the head loss, we'll multiply that by 0.04, which represents 4 feet of head loss for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. So in this example, I'm dealing with 3.2 feet of additional head through the supply and return piping in this example. What does that mean in terms of overall circulator sizing? Well, with the 7.5 gallons per minute, or 5 gallons a minute rather, 5 gallons a minute, I have 2 feet of head loss through the heat exchanger plus 3.2 feet of head loss through the supply and return piping. That means I have a shade over 5 feet of head in that entire run. So with a 75,000 BTU boiler and with the corresponding output I would get from that, I need a circulator that's going to do 5 gallons a minute at a little over 5 feet of head. If I was going with the 141,000 BTU boiler and I'm pumping 10 gallons a minute, I'm going to need a circulator that's pretty much twice as big. It's going to be 10 gallons a minute at a little bit over 10 feet ahead. All right, 10 gallons a minute at a little bit over 10 feet ahead. So so you see how that's going to affect both my circulator sizing and the output of the boiler, or the output of the tank. So let's take a look at what that all means. All right, let's take a look at what that all means in terms of circulator selection. All right. Here we show, I want you to focus on the blue lines for the
Lost the presentation, John.
Oh.
Yeah, you skipped down or something.
The presentation.
There you go.
There we go. How about that? Must have hit the wrong button. All righty. So pay attention to the blue lines. That's the 0015. That's the Taco 0015 standard efficiency AC circulator. It's a 3-speed circulator, and it's those 3 pump performance curves kind of they're generic in the hydronics industry, in the AC 3-speed pumps. The Grundfos 1558, the B&G NRF 22, and pick a pump. They all pretty much have the same performance curves as the 0015. So we take a look at the 0015, and our first example was 10 feet ahead. I'm sorry, 10 feet ahead at a little over 10 gallons a minute at a little over 10 feet ahead. If we take a look at that, we see that that's right on the sweet spot of high speed, also known as contractor no callback mode, right? So 10 gallons a minute, a little over 10 feet ahead. There we go. We've got that sized. If we're using the 141,000 BTU boiler and we're trying to get that full performance out of that hot water tank. Now, with 75,000 BTUs available, the best we're going to do is that 1.67 gallons per minute of 140-degree water, right? And we've sized that circulator at 5 gallons a minute at a shade over 5 feet ahead. You see now we're looking at that same circulator, but at low speed. We gain no benefit from setting that pump to run at high speed, really. It's not going to help our recovery or anything. In fact, we're pretty much right on that low speed line. So you see the difference both in performance, but also in circulator requirements. All right, in circulator requirements. So we're going pretty good there. We're going pretty good there. In this example, the way if I were piping this thing up, I'd probably use 3/4 inch pipe. That would be about the max I'm going to get. All right, at 5 gallons a minute, it's about as much as I'm going to get through 3/4 inch pipe before running into velocity issues. Okay, and that'll work as long as I have the pump set up properly. In this case, at low speed, I've got more than enough pump. I'm going to be working here just fine, just fine. Let me know if that makes some sense to y'all. Okay, if we went with 1 inch pipe at 5 gallons a minute, we're probably going to have a little bit lower head loss. Well, not probably. We're definitely going to have a little bit lower head loss. And again, low speed is going to be more than enough. In this example, with 3/4 inch pipe, that's about as much as we want to go with 3/4 inch pipe. We're going to be fine in either case. Just understand 1.67 gallons per minute worth of recovery, 134 gallons first hour rating compared to 212. That's the difference in the BTUs available at the boiler. All righty, again, caveats galore here, but just things to make sure we understand. We're storing at $1.40 and we're mixing at the fixture. So again, that 134 gallons over that first hour is if we're trying to take a bath in really, really hot water, okay? We're not, okay? We're going to be mixing at the fixture. So that's going to extend what we can do to a certain degree. Again, it depends on how hot of a shower somebody wants. That 90-degree temperature rise is really worst case. So middle of summer, or you're in a warm weather area where the water just never seems to get all that cold, well, you've got a lot of fudge to play with here. You got a lot of room to play with. The 90-degree delta T is the worst case scenario. And obviously your usage varies. How long of a shower can you take? How long of a shower do you need to take? These are all questions. So anyway, this is just some math, some numbers. In the handout section on your control panel, you will see a handout. There's a handout section there. It says handouts 1 of 5. There's one image that you can pull down that's going to have a bunch of these math formulas on there for you for your use. So here's some caveats. And if you were to find that you had an underperforming indirect, or really an underperforming any kind of a water heater, are there steps that you can take to kind of enhance its performance, meaning get a little bit more out of it, all right? So kind of extend that drawdown, if you will. And that's when we look at tempering valves or mixing valves, okay? Taco's second product ever from 1929. It was your basic mixing valve where we mixed cold water with hot water to get a mixed temperature water, all right? Tempering valves can certainly help expand the usable capacity of a tank, all right? Simply by mixing at the tank is kind of the same thing as mixing at the fixture, but it kind of gives you a little bit more wiggle room. Okay, what it does is it makes the tank think it's bigger than it really is. All right, and there's a two-stage math formula here. This is stage one, two-stage math formula. The first stage is to find out something we call the storage factor. And with that, you fill in the blanks here. T mix minus T inc divided by T stored minus T inc equals your storage factor. Well, what the heck does that all mean? Well, T mix, that's the temperature of the mixed water, the water that's leaving the mixing valve that's going out to the fixtures. T inc is the temperature of the incoming water, the water that's coming out of the ground or coming in from the city. So that's your incoming water. Divide that by the temperature T stored, that's the temperature of the water you're storing minus the temperature of the incoming water. So T mix minus T inc divided by T stored minus T inc equals something called the storage factor. That's step one. Step two will come in a second. All right. So to create capacity, let's take a look. Let's say our T mix is 112 degrees minus the T incoming, which is 50. Divide that by the temperature of the stored water, 140, minus the temperature of the incoming water, 50. So T stored minus T inc divided by, T mix minus T inc divided by T stored minus T inc. All right. We'll explain why that 140 and 112 in a second, but I just want to go through the math here for you. So 112 minus 50 is 62, and 140 minus 50 is 90. 62 divided by 90 gives me a storage factor of 0.69. Well, what do we do with 0.69? To figure out our tempered capacity, we're going to divide the usable capacity of the tank. The usable capacity of the tank, we're going to divide that by the storage factor. In this case, our 0.69, and that's going to give us our tempered capacity. So usable capacity divided by storage factor equals tempered capacity. And in this case, 34 gallons divided by 0.69, that gives us a tempered capacity of just over 49 gallons, just over 49 gallons. What we've done here is we've increased the capacity of that tank by nearly 50%. All right, simply by adding that. Now, Dave, would you like to explain why we went with 112 here for an incoming or for a mixed water temperature?
Right. The mixing valves typically come set and depending on where you are, locked in at 120 degrees. So so the 112 seems a little low for a lot of people out there. And the reason why is, for our example, is, some people are going to set their indirect tank for 140 degrees and say, all right, I'm good to go. Or lower, or leave the tank set for 120 and have the mixing valve also at 120. Which is not a good idea. Now, depending upon the mixing valve and which one you have, for the basic example, or the more popular thermostatic mixing valve that we have, has a requirement of 27 degree spread. All right, as a minimum. So we kept the tank in this example at 140. So we ended up having to lower the supply water temperature in order to get the mix valve to operate the way it's supposed to, in that thermostatic element. Some of them can be got down as low as 10. Some of them are down to as low as 5. So just make sure you pay attention to what you have valve wise, and look at your different temperature requirements and settings that you have in the system itself.
Yeah, it's another thing to keep in mind. Always know what you're holding in your hand and what are the requirements, because we have mixed valves that have a 10 degree minimum spread between the hot in and the mix out, and we have others that require a 27 degree spread. So you've got to know which one you're holding in your hand. Otherwise, you're going to get sandwiching, meaning the water's going to be hot, then it's going to be cold, then it's going to be hot, then it's going to be cold, it's going to drop, it's going to go. It's not. Again, you're not going to get the performance that you really want. So again, make sure you know what you're holding in your hand. That every one of these things has a little spec sheet that comes with it, a little piece of paper called instructions. Okay. And in the instructions, it'll tell you what that temperature spread is, so you can actually install it properly and set it up properly. So in this case, like I said, we've increased that capacity by nearly 50%, But hey, let's go crazy, man. Let's say we have a real underperforming tank. We got a problem here where they can't take a shower. I mean, maybe they installed one of these, multi-jet showers where you and 4 of your closest friends can all shower at the same time with water coming at you in every which direction or whatever. So let's get kind of crazy here and see what happens if we needed to really impact the stored capacity here, the usable capacity. So what would happen if, instead of storing it at 140, we boosted that temperature up to 160? Yeah, it's going to use more energy. The boiler's going to work harder. It's going to use more energy. That's not the problem. The problem is they can't do what they want to do with the domestic hot water, right?
Right.
Listen to the customer, right? What did they say? We don't have enough hot water. All right. But of course, we can give them all these other options. Oh, we can put in a bigger boiler. Oh, we can rip out the tank that you just put in, a couple of years ago, because now things changed and we put a new tank in. So all of a sudden, all these expensive options come into play. Here is another option. So take a look. This is really cool.
Yeah. So let's say instead of storing at 140, we store at 160, which we can do. How does that change the equation? Well, 112 minus 50, that's still 62. Okay. 160 minus 50, now that's 110. 62 divided by 110, that gives us a storage factor of 0.56. So we multiply that 34 gallons of usable capacity, or divide that 34 gallons of usable capacity by 0.56. Now we have a tempered capacity, or a mixed capacity, of 60 gallons. And 60 gallons is the same usable capacity as an 80-gallon tank. So presto changeo, we just turned a 45-gallon tank into an 80-gallon tank, more or less, okay? Simply by tempering and storing at a higher water temperature. So it's a great and very simple trick that you can use if you have a situation where your customer says, I don't have enough hot water. I don't know what to do. What are we going to do? Do we have to put in a bigger tank? Do we have to put in a bigger boiler? Do we have to repipe the whole thing? Or can we simply store at a higher water temperature and add that mix valve? A much simpler and a great, as James said here, it's a great way to look like a hero to the customer, right? And that, the only way you're going to know that is you got to know how to do the math. It is amazing how many of these problems wind up being math problems. It's simple arithmetic.
I did this in my house. So my house that I'm in right now, new boiler, new water, new indirect tank went in, and it was actually my in-laws' house, and it was only the two of them. All right. So we put in a small indirect tank. Well, a couple years go by, about 5 years goes by, and we put an addition onto the house. They needed to move into a handy, accessible location. So they went to the first floor addition that we put in. My family moved into the house. So now a heating system, an indirect system that was designed for 2 people is now 6. Ruh-roh, and I had a 4-year-old system. It was 4 or 5 years old. That was it. I wasn't ready to rip it all out and redo it again. Yeah. Do I know people? Do I know, get equipment, things like that? Sure. But all I did is crank it up. So I do operate my tank at 160 degrees. I got about 115 sending out to the house itself, and no complaints whatsoever. So I got all the hot water I need until that time comes when I do need to replace and upgrade, and then I'll consider it at that point.
All right. There's two ways of looking at this, especially if you're looking at sizing your boiler for the heating load as opposed to the domestic load. Let's go way back here. If you're thinking about sizing your boiler, do you size it for the domestic load or the heating load? You can size it for the heating load, but you may need at that point to install a bigger tank. Just think about what you have for a dump. All right. Meaning, do I have a big tub that they're going to use, and I want to make sure I have enough water in that tank stored at the temperature that it needs to be stored at in order to fill that tub to make it usable? That's going to be question number one. So I could make up for it with a bigger tank, okay? Or again, if I'm okay with the rate of okay with what the stored capacity of that tank and the recovery rate, and I want to make sure I can extend that a little bit, well, that stored capacity, well, then I can mix at the tank. And in many cases, it's probably a good idea to do both, right? When you're looking at it. So I hope this was helpful for you, gang. Just again, the formulas that we went through today, they're all in that handout, in the handout section. So please download this. This is the slide you're going to get. To figure out your usable capacity, it's simply tank capacity times 0.75. We'll give you a rough estimate for most tanks, okay? Your rate of recovery equals your boiler output divided by 45,000, let's call it. Your DOE boiler output divided by 45,000, that gives you your rate of recovery. The usable capacity plus recovery is your first hour rating. All right. After that first hour rating, all you have is recovery. If you're going to run it nonstop, okay. If you're going to run it nonstop, and to figure out how a mixing valve or a tempering valve impacts your performance, okay. Step one is to find your storage factor. That's T mix minus T ink divided by T stored minus T ink. So temperature of the mixed water minus the temperature of the incoming water, divided by the temperature of the stored water minus the temperature of the incoming water. That gives you your storage factor. And then you divide your tank, your usable capacity by the storage factor. Divide the usable capacity by the storage factor, and that will give you your mixed capacity or your tempered capacity with the tank. All righty. Jump in, people.
John?
Jump in, people. Yes, go ahead.
And I got distracted, so you might have mentioned it, but I didn't hear you anyway. Another good reason to keep those tanks a little warmer than most people store them at is this thing that we're still dealing with and will forever, is Legionella, right? We store that water at 140, man, we kill the bugs. The critters aren't growing in the tank. We still have to worry about them out in the system, but at least that tank is going to take care of it. At 140, all those bugs die in 32 minutes. So we've done a good job. But people that store their water heaters at 120 or 115 or something are potentially in trouble. And again, Legionella, it kind of acts like a cold, kind of affects your respiratory system, kind of like you got a flu or you got a cold. Some people, a lot of people have had Legionella and don't know. A good, strong body is able to overcome that. Their defense system will fight it, but you get an elderly person that has issues with their breathing, or some children that got asthma and some other things. Legionella affects everybody, and it's all a matter of jumping in the shower and breathing those little particulates in your lungs. And now that we're talking about particulates like we are, it just brings up another reason to keep that water heater at a temperature that's going to help prevent the Legionella bacteria.
Very good. Very good. A couple of questions here. One was about most of the specs show 180 and 200 degree water. What about, how do you figure your performance with let's say a lower boiler water temperature, let's say 160? Now, Rick, I think Rick, you've had an answer for that in the past, have you not?
I'm sorry, say again.
If you had 160 degree boiler water instead of 180 or 200, how does that impact the performance of an indirect?
Okay, for recovery's sake, it does impact it. We'd have to go to the manufacturer that's done the log mean temperature differential calculation. I can't tell you that off the top of my head, but the manufacturer will either give you a deduct, a percentage to take off, or will actually show you what that new recovery rate would be at that lower boiler water temperature.
Right. And most boilers too, you don't, again, you don't necessarily have to have that boiler water jump up to 180 or 190 for your indirect to recover. It's a good idea because it'll recover quicker. It'll recover more, but it's not necessary. More often than not, I've seen, if you're going to use that scenario, you definitely need a bigger tank. You definitely need a bigger tank. And another couple questions here. Legionnaires, what about the supply lines after the tempering valve? Enough activity and flow okay? Stagnant or not, often used in pipes in danger? Yeah, that's always a question. And Rick mentioned that specifically. Keeping the water at $1.40 in the tank kills it in the tank, but what about afterwards?
Right.
In residential applications might not be as critical. Not to dismiss it. What we do see in commercial applications is a requirement for tempering at the fixture, a mix valve at the fixture itself. So the water, so we kill the bacteria in those supply lines, because those cases the water might not be used as regularly as it might be in a residential application. So let me, that's, if that is a concern, there are point of use mix valves, so you can have that water really hot, and then it'll kill things in the line if that is necessary. Again, we see that commercially more than anything else.
Yeah, the Legionnaire's bacteria thrives at 112 to 95 to 112 degree water. So if you've got stagnant pipes in the house, the water temperature is actually going to be room temperature. It's going to be 70 degrees. So the bacteria is not going to be thriving at that point if it happens to be in the water system itself. So if you've got dead end legs or something like that, or not used a lot, that, you're not going to have to worry about it there. But if we had the tank at that high temperature, like Rick was saying, well, we didn't introduce it to the pipes. We disinfected it, or we killed it in the tank itself before it distributed out to the house. And that's, sometimes even going hotter in the tank is going to help disinfect what's going on. And that's another whole, we can spend on an entire class on just Legionella. So
That's right. All righty. That ends the official part of the presentation, gang. We do appreciate you being with us. And again, any more questions that you might have? Well, here's one. Where is the tempering valve piped in the system? I'm going to kick that one to Rick. Where is the tempering valve piped in the system?
Well, we were just talking about it. I mean, if we put it at the source, it's at the water heater, and we have some sketches. Our mixing valves give you a nice black and white pencil sketch, and there's some other things that we could send that are kind of some colored drawings as well. But they typically go out of the water heater, come out of the water heater. A lot of times you like to see them with about a 12-inch thermal trap. So they come out of the water heater, back down to the mixing valve, then out to the fixtures. That just keeps any migration of hot water. Typically hot water will not migrate downwards, right? Nowadays, with all the check valves that are in these things, some people will argue that. But if it's at the source, if it's one of those 1017s, ASSE 1017, that'll typically go at the source. David mentions the point of use, the 1070s, will go out at the fixture. So again, depending on what you're trying to do, will determine the location of that mixing valve.
All right.
So
and you also
I've
see
also included a link out to everybody. So in the chat section, I included a link to where the mixing valves are, and you'll find the instruction sheets there. And I also included it in the questions here too. You'll see that link.
Excellent. Very good. Very good. You'll also see more and more mixing valves that can actually be screwed right into the hot port of the water heater. And there'll be a port there to bring in the cold water, and then a mixed port that goes out, as well as a recirc port for domestic hot water recirculation,
Yep.
all in one valve, which is kind of cool. All righty, keep those questions coming in. Any Christmas gifts for Taco for attendees? Yes, yes. In the handout section, there's a JPEG of the math formulas that you're going to need, and that's done with our compliments. Ho ho ho. Yes, and for one lucky contestant, a new car. I got to come up with a trivia question, but hey,
Yeah, yeah. I was going to say nobody jumped on that one right away.
Nobody jumped on that one. All right.
My car's not new anymore, so.
Oh, God, it was Dave's car too, by the way, too. I was going to give away Dave's car.
The Bumblebee car.
Yes, we got to get rid of that thing. All righty, folks. One last call for questions. Again, really appreciate the gift of your time today. And let me know, is this useful for you? Did you get some good stuff out of this? One of the things we've really strived for this year, with all the restrictions placed upon us, we haven't done it, and we've done very few, if any, face-to-face trainings this year. And this has been our avenue to meet with you guys and to interact with our customers. And we do appreciate the opportunity to do that, and very much appreciate the gift of your time to be with us. So I hope everybody out there is really, really safe. Stay healthy. Use your head this holiday season. Don't want anybody getting sick. And on behalf of everybody at Taco, I just want to wish everyone the happiest and most joyous of holidays. And I hope you and your families are all safe, healthy, and get plenty of presents. Presents are always good. Aren't presents good?
Beauty.
Yeah, except for January.
Except for January. January is not a great present. Lauren, yes, we will be
bills
continuing.
No, January. Yeah, the presents are nice in December. Then the bills in January, yeah, it's horrible.
There you go. There you go. To answer Lauren's question, yes, we will be continuing Taco Tuesdays. Be two classes per month. One on a more commercial focus, and then one on a more residential focus. So we'll be doing two of those a month, every other week. And we will be starting at some point in January. We'll have a return of Taco After Dark on Wednesday nights. It should be an 8 to 10 week session that should be nothing but fun. So hopefully you guys can join us for that as well. Because these are a little more formal. Taco After Dark, we let the hair down and we get a little crazy. All right.
What hair?
Well, I let my hair down. Dave and Rick just no, obviously not.
No.
Right.
All righty, folks. Hey, thank you again.
Right.
Any
Y'all
final
take
words,
care.
boys?
Keep doing what you're doing out there, people. Keep learning. Never let the cement harden. All right. So that's the best thing about coming to these things. You know, that cement, once that cement hardens, then it's all right. I guess it's almost time to retire, you know, and hang up the wrenches if you're out there twisting wrenches still. If you're out there designing, troubleshooting, things like that. Yep. Never let the cement harden. Yep. I know John has a different twist on it from what his father says all the time. What's your father always? I can never get it exactly the way you say it.
Oh, my old man used to tell me it's what you learn after you know it all that really counts.
That's right. That's right. Yep.
So, and hopefully once we know it all, that'll be just the day before they nail down the cover of the box.
That's right.
And we go down for the last time. So, hey guys, thank you so much. Have a wonderful holiday. And Dave and Rick, we'll talk to you in a couple hours. So take care.
Yeah.
Guys.
That's right.
Take care.
So long,
Enjoy,
everybody.
y'all. Happy New Year.